Hey there, and welcome to this new week of Ground Zero, wherein we'll dive and discuss and dissect linear regression and its main ideas. So before we jump right in, we want to know why you want to do linear regression in the first place. So at its core, this is more about regression is about predicting. So if we are given a value x, what does it say about the value y? For example, if we are given the number of sales for May, can we predict the number of sales in June? It also can tell us about the linkage between two variables. For example, to recall a good one, I think, yes, you might have known this equation for gases, wherein it was established that volume and so I think the variables in question would be pressure and volume. So it was discovered by Boyle that pressure and volume have an inverse relationship, which is now called the Boyle's law. And empirical studies like the one Francis Galton conducted in the late 19th century. So his hypothesis was that he had a theory that if we were to breed successive generations, taller parents would produce taller children. So this could be used for selective breeding of taller parents and the taller children and their taller children over the years, thereby leading to accentuation of certain human traits or the betterment of I think our phenotype. But much to his chagrin, it didn't turn out quite well as he was expecting, because it was found that the children of these people, of these very tall people, were taller than average, but not necessarily tall, or not necessarily taller than the parents, which led Boyle to write a paper about regression. And that was indeed the first time this word was actually used. Now, when you talk about this, before we jump into the parametric formulation of this problem, I think it would be worth exploring or getting to know the terminology for this. So the variable used for explaining something are called explanatory variables, or regressors, or independent variables, or in usually statistical circles they are called covariates, or also predictors. So these are like 5 names that you might hear in the wild for this the word explanatory variable. So and the variable to be predicted is called the response or the dependent variable. So these are usually denoted by big X, and this is denoted by the small y. So now I think this is probably the most seen equation of all time. This is the equation of line. So parametric, because there are 2 parameters, a, which is the slope, and b, which is the y-intercept, also known as where x is 0, also known as rise over run, delta y, delta x. Okay, so now let's imagine you have a data cloud here. Okay, sorry for the, I guess, rough or more rustic drawing, but the idea is to what line would best fit the data. And this is, of course, this fitting of line as a premise came to be because we also wanted to predict all these things. So this prediction, linkage, empirical studies are all rooted in some sort of finding out about what happens when this is this. So yes, this is the very naive approach, and let's formulate it even further. I'll speak what this is. This is a let's say a wall where this W or this weight is being suspended. This is a spring of length L. We have been told that A and B are fixed, and we get this equation Y is equal to A plus BX plus EI. Now, you may ask, what is this? For every experiment, we assume that there is some error which through, I guess, exogenous conditions or the natural setting of the physical experiment introduce themselves. So this is what we get. These two are fixed, and this is the weight we can set to measure this phenomenon. So this is, we can do it for the ith times. This is I plus bxi plus ei. And about the errors, we assume that they are independent and identically distributed. So not to say that these are identical, but the underlying distribution is identical. And why do we do that? Well, it's a very intuitive, I suppose, surmisation that if we have similar errors, right, none of them would be positive or negative, nor would one be contingent to the other. They're completely random. No error in the I-1th iteration doesn't influence the error in the ith iterations. And also this is normally distributed with standard sigma. Yeah, normal, because that's the most common distribution found in the wild, and this is also this also occurs in the wild. So yeah, and now this is about optimizing the line which minimizes this MSE. So let's talk about this a little bit. Mean squared error. Okay, so let's say a line here. This is data point here. This is data points here. So if you, as you can see, it is very poor. So the distance between this and this is very high, and this is what represented by this quantity. And least squares technique is just a minimization of this problem. So I'll try to perhaps quickly walk you through this. So let's say we have this problem and we have to minimize the error, right? So we are going to set the stage by setting the partial derivatives of S and A. Partial derivatives of S is with respect to A, and partial derivative of S with respect to B, both equal to 0. Now, why partial derivative, you might ask, and if that's a genuine question, by the way. So this S is a function of both A and B. So we want to see that when we change S, or when we make slight changes in A, while keeping B fixed, what is the change in the slope, or what is the change in the error? So that is the premise of this exercise that I'm about to show you. So this is what you get: ds by dA yi minus a plus bxi squared. So we let the inner function be u. This is a very plain vanilla usage of the chain rule that I think many of you might know. If you don't, that's fine. I'm sure you know the power law. So we get u squared, and the derivative of u squared is just 2u. So 2 times yi minus a plus bxi. This is what we get. Now it's time to derivate the inner function, the chain rule, as I said. So if you can see here, we're giving this expression, and during partial derivation, all the variables except the variable with which respect to this derivative is being computed remain constant, and therefore can be neglected. So imagine this. This is the variable, and we have x. So wouldn't we get 1 here? Similarly, with respect to a, this inner expression would yield negative 1, right? So this is what we get: minus 2 yi minus a plus bxi equal to 0. Now if you see here, this can be removed because minus 2 is not equal to 0. So we can just divide by both sides by minus 2, which yields us this expression. Thus bxi is equal to 0. Now if you might know your sigmas, and everyone is a sigma here, sorry, that was a poor joke. Anyway, so it breaks at positive and negative operations. एडिशन और subtraction में टूटता है. It doesn't hold for I guess it doesn't hold for multiplication and division. So what we get is sigma I 1 to n yi minus the same for a plus same for this to be equal to 0. Now if you notice that this a and b are constants, sorry, so we get this remains the same. I'm not gonna write it na, because if you add something n times you get na. That's very, I think, obvious. And then b and xi. So if you solve for a, meaning basically rearrange the equation, you get na this, right? And divide by n, you get finally dude, sorry, my headlighting is getting progressively bad. Anyway, so we recognize this as the mean. So a hat is given by the mean minus b times x bar. So this is the expression called the estimate for the intercept, estimated intercept. And similarly we can derive b hat, but I think it should be rather left as an exercise for the viewer, because I think this is the same principle. You have to equate ds by db to 0, and I admittedly that it requires much more algebraic heavy lifting than this particular this thing, but I think it's a worthwhile endeavor for you to do, I think, on your own, and it will instill, I think, great confidence. And mathematics and ML, from what I've learned, is all about these aha moments that you get while working through these nitty-gritties and getting really your hands dirty behind every algorithm. But I will give you the formula for it, and please check if you are deriving this. See if you get the same results here. Xi minus x bar so this is also very similar looking expression, which is covariance of xy times variance of x called beta hat. And similarly we know we do have a idea of what the estimate variance of the terms is. Estimate sigma squared, that would be 1 minus n by 2 . So this formula accounts for the fact that we have estimated two parameters from the data, and hence we have lost 2 degrees of freedom, and that is why you have n minus 2 in the denominator. I think there's that's a question that I had a lot of the times, and this was always, people struggled to understand why it was n minus 2 and why it's n minus 1 in some of these sample covariances and a lot. But yeah, this is the reason why for this case, once you derive this, I think this is a fairly straightforward derivation, I reckon. Now let's move on, and let's talk about the properties of least squares. And this will be a little bit I guess not very straightforward, but it is important to know, in light of seeing in not to extend it and make it very mathematical, the properties of least square, it is very helpful, because the alpha hat and beta hat, which we have derived just right now, are like unbiased estimators of alpha and beta, which, yeah, as you can see here. So the saying is, if you do it a good amount of times, the alpha hat will converge to alpha and beta hat will converge to beta. These are the variances for alpha hat and beta hat. This is a very intuitive formula. When you see that amount present, it is like a very proportionate relationship with the amount present in the measurement. Measurement in the sense, like, imagine the physical experiment that we were doing and this was the variance. This is an example of higher variance because you have no idea of where to fit the line, right? Let's say points are clustered and there is a very uh, ellipse size. I think the ellipse is not very elongated in this sense. In this sense it is, and this is why you will be more confident when I guess naively or visually fitting a line through across this data cloud. Okay. And similarly you have v beta hat. So we have studied, usually there is asymmetricity about this regression problems, and it is x and y. Usually we have been doing y on x so far. So it is nothing except the fact that you switch the problem, and where you are now estimating for x. So x hat becomes a1 plus b1y. Remember the y formulation was this. And from our earlier derivation here, you get that beta 1 is covariance of xy times variance y, because this remains the same. If you remember, covariance xy is equal to covariance of yx, is the same thing. Okay. The denominator gets swapped and turns into y, variance of y, and this is the expression for the for predicting y given x. So this is it. And if you, there's an interesting property about this, and I have included this just to give you that aha moment, I guess. So I suppose so this leads to this formula, which causes b1 times b2, this coefficient times this coefficient, multiplying that gives you a formula for Pearson's correlation coefficient. And this can be also formulated as this way. Let me write it a little neat way. Bx given y times b y given x is equal to r squared. And these lines are always different than each other unless and until r square is equal to plus or minus plus 1 is equal to 1, not plus or minus 1, plus 1. So yeah, there is this. I will give you some hint about parametric regression, non-parametric regression, before wrapping things up. So non-parametric regression, so the assumptions of linear regression is that the data is identical and independently distributed. There are a lot more constraints in the data, so it has to be linear again. So there's that. So what non-parametric methods do is give you a lot of leeway in terms of how you want to formulate a problem to solve for your given use case, right? Say for there are methods like kernels, splines, etc., which we can touch upon later. I don't know if it's currently part of the curriculum, but we can have it added. But for this particular example, I want you to consider this for x and y, and I want to predict this. Now this is not a linear, there is no conceivable formula that you can think of. I mean, sure, you can probably break it down and do it the neural network way, but yeah, we're not currently discussing that. So there is this problem that we have. So one of the things we can do here is take a window here. So in the window, we take this, whatever the samples that we are capturing, take the average of it and predict y hat, which is called the local averaging formula. Yeah. So you can do this for here. You can measure x for here. You can dissect the data points into very small sections, which can be which can be estimated linearly with a fair amount of accuracy. right? So these are called local averaging methods, and these are obviously, the con here is they only are applicable within the range of data. So these are not very good for extrapolating further. Yes, you can take an average. So basically, you'll get a curve like this, taking a mean. Oh shit. Yeah, taking a mean of this, you'll get a curve which looks like this. Yeah, it'll smoothen out essentially, but it is of no good beyond this, beyond the range of this data. Like let's say here and here, you cannot say anything about the y occurring here or anything like that. So this is a twist of non-parametric regression, which you can use. There are weighted methods or weighted distribution methods. Which will essentially ascribe higher amount of weight. Then there's a threshold, and points above that threshold are ascribed a higher weightage, and the points lower than that are ascribed a lower weightage. So this would be a taste of the non-parametric side of regressions. I think there is a lot more ground to cover in terms of how regression is, but for the fundamental ideas, I think this is more than enough. All you have to do understand is regression is nothing but finding a best fit line to fit the data, and the way to find the best fit line is through the least squared method, ordinary least squared method. Okay, there is also a you can use linear algebra to do the same, but I think it's currently not a part of this paradigm, where the idea was to give you mathematical intuitions about why we do certain things. And I think there have been, I think I have given some leads for you to follow for people who are initiated and have the proclivity to do that. I urge you to do it. It's a very, very vast, very beautiful topic, and I think it's almost endless in that sense. There is certainly, we can talk about regularization, and then there is again kernels and splines, which I've not touched upon because they are part of a non-parametric paradigm. So the idea was to give you an idea about simple linear regression, which can be certainly extended to multiple linear regression. So yeah, I hope you like the video, and do let me know if there is something you need me to touch upon, and I can perhaps try that. Yeah, thank you for watching, and I hope you have a good day. Bye bye.